So again, the way to think about this in some sense is like a Fourier series where I've got some function and I'm splitting it up into a set of useful constituent functions, not sines and cosines. They're more complicated, but they have a lot of properties. Namely, they have this property. So the YLM itself. So basically, when you get to through quantum, the way you start thinking about it is because I have two variables, I have two dimensions, I have to have two so-called quantum numbers. So I got to label these with both L and M because I have both theta and phi. And when we had just like the normal Legendre polynomials of cosine of theta, they just had L on them because we were only worried about theta. But these have associated Legendre polynomials. You can get one from the other. The way that it'll work in practice, on the homework, you guys have at least one problem where you're told to go through Rodriguez's formula or some of the recursions, but in general, you just like look these up. And there's a normalization. So NLM is chosen such that this is true. And I'll write it once while I have notes because I honestly can't remember it. There's like some funky, I always get the factorial part right and the other part wrong. So big square root 2L plus 1, which is the part I should get right, and then 4 pi, it's the part I should get right but don't, and then L minus M factorial, L plus M factorial. Okay, so this is the normalization, and the whole point of the NLM is so that this is true. So for the 43rd time, what should this be equal to? And we're using the shorthand, we're integrating up over the whole sphere. So Kronecker deltas. So this is the point of this gross normalization constant, is that these make a complete basis. And note that this star means complex conjugate, because as you see here, we do have complex valued things. So that's a complex conjugate. Okay, so again, same idea, but technically more difficult. So those are spherical harmonics. Let's do an example of how this would work in practice. But any questions about any of this before we do that? Okay. And you know, the way that at least we work with them for the most part is that you think about yourself as like kind of a spherical harmonic auto mechanic, is that you don't have to build the things, you just have to know how to use them and fix them. So deriving them, you know, not a big deal. Learning how to go and look up tables of spherical harmonics, knowing some of their properties, and most importantly, knowing easy ways of expanding stuff in terms of spherical harmonics is what we want to do. So let's do an example. And I'll do this first quickly in the silly way, just to show you how it would work, and then we'll do it the not silly way. Maybe you guys can figure out how that would be done by the time I finish this. So let's take something kind of reasonable. Need a function of theta and phi. And let's do something that looks a little bit pleasant. So 1 plus sine theta plus, times sine phi in terms of spherical harmonics. Okay, this is first method. This is really just like brute force. And the idea is that if I gave you a function of x and asked you for the Fourier series decomposition, the collection of a's and b's, the coefficients I would need, you would just dutifully write down what it is and then compare. So what I want is, okay, 1 plus sine phi sine theta is equal to a sum from L equals 0 to L equals infinity, and a sum within the sum of m equals minus L to L of some coefficient NLM YLM. Oops. Okay, what's the problem with this? I mean, it's not like a mathematical problem, it's more of like a time constraint problem. How many YLMs do I have?
Quite a lot.
Yeah, which is weird because you had quite a lot of Fourier series or Fourier, you had an uncountably infinite number of Fourier transform coefficients. The problem is that with the Fourier series or the Fourier transform is that they all look the same. They just have like some undetermined coefficient. I just have like a sine n pi x over L or something like that, or cosine n pi x over L. So I just left the dummy variable. The issue here is that when I look at the table of Fourier coefficients, so hopefully I have this up. Yeah, so I look at a table of spherical harmonics, is that they all look different, right? Okay, getting towards the nicer way of doing this, I want you guys to stare at the table of spherical harmonics and notice some trends about the m's and the l's. So the L equals 0 is just, essentially constant. This constant is chosen so that when I square it and integrate over the whole sphere, it's 1 over 4 pi. Whole sphere has 4 pi. Unit sphere has 4 pi surface area. So that works. But then, okay, I have m equals minus 1. I got e to the minus phi. M equals 0, no e to the phi. M equals 1, e to the plus phi. Sine theta, cos theta, sine theta. Sine squared theta for L equals 2, sine times cos, cos squared, sine times cos, sine squared. So just kind of notice some trends. But what I would have to do in the brute force method is I would have to just sequentially go through, maybe starting with L equals 0. L equals 0 has 1 term, L equals 1 has 3 terms, L equals 2 has 5 terms, L equals 7 has, L equals 3 has 7 terms, and just keep going until I like run out of function to associate. So this would be the same way of, representing a vector in terms of some basis, and I keep dot producting with basis vectors until I basically run out of function. So I represent the whole thing. So obviously this is the least efficient way of doing it, but that's what we'll start by doing. So first we'll see how much of this overlaps with y00. Okay, so the way I would do that, and we'll call this n00. So that's what I want, how much of this overlaps with n00. I compute by the same kind of overlap integral. So it looks like this. So unit sphere again. And then I look up what that is in the table. So integral over a sphere is 0 to pi, 0 to 2 pi. And then y00 itself is, I don't like the way Wikipedia writes it, 1 over root 4 pi is the nicer way of writing it. Technically the complex conjugate, but that's real, so no biggie. 1 plus sine theta sine phi. And then integral over the sphere is, unit sphere is sine theta d phi d theta. Okay, and I just do that. So multiplying through, what I get is a sine squared theta And honestly, you know, that's just a constant, so let's put it up front. Multiplying through, I get this. I can do these integrals. Again, I'll go like pretty fast. My argument is that this is an even function, that's an odd function, so the second term goes away. I just end up with 2 pi times sine theta. So 2 pi from the integral, still have root 4 pi, or root pi there, and then get 0 to pi sine theta d theta. And then after I get that, I end up with 2 root pi because that's 2. Okay, it's a little bit fast, but I just take the overlap. And then now what I know is that because this coefficient didn't vanish, is that contained within my function, there is some of the first spherical harmonic. Right, so this does contain some y0, 0, which means we've made some progress, and there's only, you know, so much of the function left to represent, and we've taken out one of our possible infinity terms. Okay, so I will keep going. So the next term would be y minus 1, 1, I guess. Kind of depends on how you want to count. I'll erase all this and change whatever I need to change. So now I have y minus 1, 1. And then that would give me n minus 1, 1. So 1 minus 1. We should do Lm. And then Lm, complex conjugate. And then I would just go and look up in a table what that particular YLM is. And that's not going to fit in here unless I write really small. So I'll try to fit it in there. So the minus 1, I know that's e to the minus I phi, but then it's complex conjugated. This is literally just looking it up from the Wikipedia table. Okay, this is what Wikipedia table tells me, but because of the complex conjugate, this is the only complex thing, so that becomes a plus. Okay, this one is a little bit more difficult to do. What I could do if I didn't feel comfortable with the exponential is I could use Euler's formula, and I could represent this by, you know, cosine phi plus I sine phi if I wanted to, and then there's just like a I out front, and I could use the same methods. But the point is that you're just going to see over and over just trig integrals. And to be honest, if you did have to do one of these by hand, kind of halfway, all you would end up with is sine squareds, cosines times sines, 3, 4 power, dot, dot, dot. So again, I'll go like kind of quickly through the integral, remembering we have this extra sign from the piece of area. And then I'll just say like dot, 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 go through this. And what I end up with is I root 2 pi over 3. Okay, and we would call that n 1 minus 1. Okay, the next one I would do is y0, 1. And that would tell me how much overlap I would have in between the 0, 1 spherical harmonic, which would look like this, 0, 1, complex conjugate, f d phi. And then writing out that integral, and then pulling that out of the table of spherical harmonics, and multiplying that by my function, and then integrating up over the sphere. I'm definitely not going to do that one because that turns out to be 0. And working really hard for 0 in such an integral, I think, would be a little bit heartbreaking. And then I would keep going. So then I would do 1, 1, and then that would tell me 1, 1. And at this point, you probably start getting a little bit bored because you see that we're just going to keep doing this sequentially, but that turns out to be not 0, so that gives me an I root 2 pi over 3. And then I would have to keep going, and then I would do y minus 2, 2. So we've done all the ones. And the y minus 2, 2 term would be equal to 0. And then the y minus 1, 2 term would be equal to 0. And then the y 0, 2 term would also be 0. At what point would you guys tell me, like, please stop? So there are two ways of, well, actually, sociologically, there's three. You'd just be like, I'm sick of this stuff. But there are two ways you could tell me that I need to stop doing overlaps and computing these integrals. One way you could think about maybe from a vector standpoint. The other way you could think about from just think about the properties of that table, think about the properties of the function we're decomposing. And one way or another, it turns out I don't need any of the L equals 2 spherical harmonics. So one way to know that I'm done with this is that I have the function. So I have these three non-zero coefficients. We had an n0, 0. I just couldn't fit it on the board. And I have an n minus 1, 1 and n 1, 1. I could actually take these coefficients in spherical harmonics and I could just add them up and verify that I get f back. So once I've got the whole function, I don't need to keep looking for extra pieces. I've got the whole thing. The other way of thinking about it is that I see sine theta to the first power. If you remember the properties of the table of spherical harmonics, L basically tells you the power of, leading power of the trigonometric functions. Like in L equals 2, we had sine squareds, we had sines times cosines. We didn't have anything to the third power, we didn't have anything to the first power. So once I have, I look at this and I see that I don't have any like sines to the 10th power or whatever, I don't need any L equals 10s. Right, so that's actually a less strong argument, but just sociologically, if you have something, I have sine to the first power, I probably do not need L equals 14 terms, which is great because there are, 29 of them, and I don't want to do that. So this is the hard way. And after all this work and lots of zeros, and honestly, these are anything that you guys don't know how to do, they're just kind of annoying. Just remember the two tricks are, or two kind of pitfalls are, remember to complex conjugate when you do the overlap. We have complex functions now. And then remember that when you're integrating over a sphere, you have sine theta d phi d theta. Okay, so we had n0, 0 equals 2 times root pi. We had n1 minus 1 equals I root 2 pi over 3, and then n1, 1 equals I root 2 pi over 3. And what I really hope to be the case is that this is true. So what this means ultimately is we have our spherical harmonic decomposition. And our spherical harmonic decomposition tells us that this is true, is that f of theta and phi equals n0, 0, y0, 0, plus n1 minus 1, 1, y1 minus 1, plus n1, 1, y1, 1. Okay, in the same way that when you do a Fourier series decomposition or expansion of a function, there's physics in there, like it kind of tells you what tones the function is making. When you do a Fourier series of a musical note, it tells you the pitches. If you're talking about quantum mechanics of atoms or molecules, or you're talking about, especially scattering in quantum mechanics, or you're talking about electromagnetic potentials, this is all the physics. Like the physics you just read off of like how much of each one of these there is. But anyway, I really hope this is true. So let's make sure that this is true. Okay, so I go back to the table. So I go back to the Wikipedia table and I say like, what is y00? Well, again, y00 is 1 over root 4 pi. And then I go back to the Wikipedia table and I say, what is y minus 1, 1? And these are the same. So these two coefficients, so I'll just like put everything up front. Hopefully that's not going too fast. And then I can look at what y1 minus 1 is. And again, that was 1 over 1/2 root. Everything's in the square root. Root 3 over 2 pi sine theta e to the I phi. So that was a plus, a natural, oops, sorry, we did minus first. So that's a minus. And then plus, same coefficient. And then again, go back and look up what y11 is. So it's got an overall minus sign and then all the same info. Okay, there's a lot of simplification we can do. So here I have 2 and 2 and root pi. So this whole term is actually 1. And then here we have root 3 over 2 pi's that we can pull out here, and oh my gosh, it cancels that. So I kind of chose this to be, a nice example, but I have I over 2 that I can pull out. This and this and this cancel, which is kind of nice. And then I have a sine theta that I can pull out. So I'll do that too. And then I have e to the minus I phi plus e to the I phi. And I'm going to sit here awkwardly until somebody tells me what to do with this last term, this e to the, and honestly, I'll put the over 2 there instead, because I think that's even more helpful.
I mean, that looks a lot like a hyperbolic, I forget which function, but sine?
Yes, absolutely. So it's a hyperbolic sine, but the argument is an I. So it's absolutely sinh I phi. And you can look up a property of this where sinh I phi is actually equal to a sine. The other way of thinking about it is I've got Euler's formula. So I've got e to the I phi is equal to cosine phi plus I sine phi. And then I have e to the minus I phi. And cosine is even, so the minus doesn't do anything. And then I have minus I sine phi. So what happens here when whoops, I'm sorry, that should be a minus sign. What happens here when I do this? One way or another, either the property of sinh will tell you this, or when I subtract these, cosines go away, I get I sine phi minus 2. So this is actually equal to 1 plus I sine phi, and then 2 and 2 go away, so minus 2I sine phi. And then, oops, over 2. And then I times minus 1 is plus 1. So believe it or not, this equals I sine phi times sine theta. Okay, so that was like the 20-minute grubby brute force way of doing this. Again, the problem with this is, in some sense, is that you could take one generic integral when you were doing Fourier transforms or Fourier series. Here you kind of have to sequentially go through the L equals 0 terms, L equals 1 terms. There are recursion relations to tell you what the axial, the theta part of the YLMs are. They're really clunky to work with. I just want you to know they exist. The azimuthal part, e to the I m phi, is really nice, but these are just like not as nice as working with Fourier transforms or Fourier series, like the sines and cosines. So there's really no way around this. This is tougher. But what we want to do is kind of cheat and utilize the insight that you guys had from just looking at the table of Fourier series. And this is the better way of determining, table of spherical harmonics. This is the better way of determining if you need to determine a multipole expansion or spherical harmonic expansion by hand. This is the much better way of doing it. And on this homework, there is definitely one where I would recommend this method. So the cosine 3 theta thing, multiple expansion of that, just expand the thing with a trig identity and look at what it is, like what must it be? Okay, so we now want to change this to method 2, examination. And now that I've kind of been reminded of some of the properties of e to the I phi, this will be a bit easier. Okay, so this has a constant term, and this has a sine theta term. And what I'm going to do is I'm going to look at my table of spherical harmonics. Oops. And say, well, I've got a constant term, and then I have sine terms. So what on earth could this possibly be, right? So I'll see if it's got some of that, and some of that. I don't see any cosine theta terms, so I won't include that. And then here in L equals 2, I see, squareds. I don't have any of that. And likewise, I know I'm going to go up to third power, fourth power. So just by examining the form of the function itself, it's got a constant and it's got sine of thetas. So I'm just going to see if I can express it with unknown coefficients in terms of y0, 0, y minus 1, 1, and y1, 1. And partly because this is the second time through, but partly because legitimately this is much easier. This is a nicer way of doing it. So, so 1 is the constant term. So that's got to be some constant times y0, 0. And then I know that that's 1 over root 4 pi. So I know that that's root 4 pi. And then I know that sine phi sine theta is equal to C1 minus 1 y1 minus 1 plus C11 y11. And that's a little bit harder, but I have sine of phi sine of theta is equal to C1 minus 1 And then again, just picking it out of the table. Actually, let me do this in a slightly different way. I think it's less awkward. I'm just gonna, if you guys remember what the y1 minus 1 and y11 kind of look like, just visualize for a second. What's the problem with this? Did you guys ever see a sign of phi in the table of spherical harmonics? And you kind of know the answer from last time through this, but what do I need to express this in terms of to map it onto the table of spherical harmonics?
You need to put it in terms of an exponential.
Yeah, so we'll just do that right here. So this is equal to e to the I phi plus, minus e to the minus I phi over 2I. So that's just expressing sine of theta in terms of complex exponentials. Sine of theta. And therefore that's equal to 1 over 2I. Yeah, let's put everything together. 1 over 2I e to the I phi sine theta plus 1 over 2I, and by plus I mean minus. Really having a bad sine day. Minus I phi sine theta. Okay, so this has got to be the plus term. This has got to be the y11 term, and this has got to be the minus term. This has got to be 1 minus 1. And then once I have it written like this, I can just compare it because the functional form is sitting right there. I can just like read off what the coefficient needs to be. So the coefficient needs to get rid of that 2I and needs to put in front of it a root 2 over 3. So this would be equal to, just again comparing and multiplying what I need to multiply, this would be equal to C11 times y11 plus C1 minus 1 y1 minus 1. And then that would tell me that C11, just as it did before, equals I root 2 pi over 3. And C1 minus 1 actually equals the exact same thing. So that much faster, did not involve having to look up any trig integrals. We even kind of like cheated and say like, you guys can do this. This is just literally reading off things from the table. I know that there's a constant term, therefore there should be a y0, 0 is the argument. Neither of these methods are perfect, but I think this is, for all the problems that you guys will get, this will be much easier. Okay, so any questions about that? I'll post another one. So you have a second example of this.
I had one question. It's only slightly related though. It was about kind of the inner product that we took earlier to kind of get this. And I was wondering why there was a complex conjugate in that, or if there's a simple answer to that.
Yeah, there absolutely is, if you're okay with this analogy of normalized functions and basis vectors. So let's say that I want this to be true. So I make some basis vectors, right? E1 and E2 and E3. What do I want to be true about the dot product of E1 and E1?
It should be just a scalar.
Yes. And specifically, if these are unit vectors, the scalar should be what number?
Well, 1.
1. Okay, the second I go to complex numbers, I have kind of an issue. So let's say that we live in complex space instead of just pure real space. And there's no reason not to do that with just normal vectors, aside from the fact that it's like annoying and teaching poor STEM freshmen, like they're just, you know, when you talk about multiplying arbitrary phases in the complex plane, they tend to look at you kind of funny. Let's say that I'm okay with complex numbers. And instead of 1, 0, 0, taking one step down the real axis for the x component and then no steps down the y and the z component, I just multiply by I instead. Okay. The other way of thinking about this is I'm multiplying this by a phase. So I'm just multiplying this by an overall phase if you're okay with the quantum idea. But we'll just say like, I have complex numbers. I'm okay with complex numbers in my vector space. What I still want to be true is this. I still want this to be true. That's not going to work if I say that this thing dot product with itself. So now we're saying that this is our E1. So if I dot product this, and that's I times I plus 0 times 0 plus 0 times 0 equals -1. So this is very unsavory for me. What happens if I define the inner product as E1 complex conjugate dotted with E1? All of a sudden I'm saved, because now what I have is the complex conjugate. I don't have an I, I have a -I. So this becomes -I, and then still 0 times 0 plus 0 times 0. And then that's +1. So in general, if you live in a vector space with complex values and you define any sort of inner product, whether it be functions like this, or vectors like this, whatever goes in one of the two, usually the first entry, has got to be complex valued. So in fact, this is the most basic definition of an inner product, complex conjugate of the first thing. It's just up until now, you've been dealing with real valued thingies.
Okay, that makes sense.
Okay, cool. Let me close by making one last comment about the time-independent Schrodinger equation. Because we'll also do that next in the case of the spherical, or the just 1D. There. 1D simple harmonic oscillator is, I know at least one of you guys has been through quantum. Has everybody been through quantum? Okay, cool. So we'll put this somewhere in the middle, but you've all been through modern physics and seen the Schrodinger equation. Did you guys do like particle in a 3D box and separation of variables?
I think Banesh showed us some examples. I don't know if we ever had to do that problem ourselves.
Okay. Yeah, so that's actually a good place to be. So this isn't boring. Okay. So this is one way of writing the time-independent Schrodinger equation, where H is a differential operator. Specifically, the differential operator H looks like this: minus h bar squared over 2m, and then our new friend, the Laplacian, plus the potential. And that could be in 3D, but we haven't chosen coordinates yet. And then the wave function itself is also a function of those coordinates. So this is a differential operator. The reason to split stuff, and we now know that separation of variables is like the technique to solve partial differential equations, is that if you split phi of r, so let's say you have a spherical symmetry, and what that would mean is the potential is actually only a function of the radial coordinate. So you can take the potential well in which you live and you can rotate it and theta and phi all you want and it looks the same. The only thing that matters is how close you are to the center of the thing, right? So this could be gravity, this could be like hydrogen atom, like a single proton. This could be something more complicated like a nucleus, but if it has radial symmetry, then we know that the trick is we're going to split this up into r of r, theta of theta, and phi phi, because one, we always separate variables, but two, we know that spherical symmetry means we should use spherical polar coordinates. The only thing that's different, no matter what you do, if you're talking about electromagnetism, you're talking about gravity, you're talking about, you know, some finite volume nucleus, is that if v is just a function of the radial coordinate, this is always going to have the same solution. So this is always going to be solved by the YLMs. So the good news and the reason to really stop and dig into these is that it basically solves all spherically symmetric problems. So all you do is, like you say, yeah, there's some YLMs and some other stuff. So for potentials that look like k over r, you get spherical harmonics for free, and then you have to work hard to get something called the Laguerre polynomials. So again, this is the reason to kind of dig your teeth into this particular set of solutions. I mean, for nuclear and atomic physics, they're just as important, if not more important, than Fourier series and transforms. Okay. Again, most important thing is doing a couple of decompositions and knowing some of their properties. Okay, any other questions about that before we take parallel track slightly off center to this one? Yet another really important quantum differential equation.